Welcome to our talk on OSX, one-stage 3D whole-body mesh recovery with component-aware transformer. In this work, we propose the first one-stage pipeline for expressive 3D whole-body mesh recovery. Besides, we collect a large-scale upper-body dataset, U-body, to bridge the gap between the basic task and downstream applications. Our one-stage method achieves new state-of-the-art performance on 3 datasets. Given a single-person image, our target is to reconstruct an accurate and natural full-body model, including body pose and shape, facial expression, and hand gesture. By revisiting existing mesh recovery methods and dataset, we find out 2 essential limitations in this task. The first one is that existing method adopt a multi-stage copy-paste pipeline to reconstruct the whole-body mesh. That is, they use 3 separate networks to estimate the body, face, and hand parameters, and then fuse the results, which may lead to heavy computational cost and unnatural connection between different parts. This problem motivates us to propose a one-stage method that simultaneously estimate the whole body parameters with a single network. The second problem is the data discrepancy between the training set and real-life scenes. Existing training set are either indoor single-person scenes with limited images or outdoor synthetic scenes where the people are often too far from the camera and the hands and faces are frequently obscured. However, in many daily life scenes, the upper body is a major focus, whereas the hand and face are essential for analysis. Thus, the model pre-trained on existing datasets cannot perform well in real-life scenes. This problem motivates us to build upper body datasets that concentrate on the real-life scenes. Next, I'll introduce the proposed one-stage method. Based on the observation that the body pose estimation needs the global dependencies, while the facial expression and hand pose concentrate more on the local feature, we propose a component-aware transformer. The encoder captures the global dependencies with the global self-attention mechanism and regress the body pose and shape params. Meanwhile, it provides a high-quality feature map for the decoder. In the decoder, we use several key point-guided attention modules to extract the local feature from the feature map and regress the facial expression and hand poses. The deformable cross-attention layer can be represented as the following formulation, in which key point queries Q extract information from the elements of multi-scale features V around the position of key points PQ. Next, let's look at the proposed U-body dataset. Our dataset has the following characteristics. The most important feature is that we concentrate on the upper body part and collect our dataset from 15 upper body real-life scenes. These scenes have rich hand gestures and facial expression. Besides, our dataset has a large volume with more than 1 million frames and is very challenging due to the severe truncation and highly dynamic camera views. This is an overview of the 15 real-life scenes in our datasets, including conduct music, talk show, sign language, etc. To annotate 3D human meshes from large volume online videos, we propose an automatic annotation pipeline, which can be divided into 2 parts: 2D whole-body key points annotation, and 3D simple X-fitting. We first adopt the SOTA bounding box detector to estimate the person and hand bounding box, and then we use 4 transformer-based models to predict the whole body, face, and hand key points. And then, we design an iterative training labeling revision loop to optimize the OSX model parameters and fit the projected 2D key points into the annotated 2D key points. This is an overview of our annotation results. It can be seen that we can achieve accurate annotation from the online videos. Now let's take a look at the experimental results. We evaluate OSX on the 3D whole-body mesh recovery task. We can see from the table that OSX achieve consistent improvement on Agora, EHF, and 3DPW datasets. We also bullet a benchmark on the proposed U-body dataset. We perform ablation studies on the EHF dataset to validate the efficacy of the key components in OSX, including the key point-guided deformable attention and upsampling mechanism. Now let's look at some visualization results. This is a comparison with Expose and Hand 4 Whole on the EHF, Agora, and U-body datasets. it can be seen that our OS X reconstructs more accurate and image-aligned human mesh. For the code, dataset, and more information, please check out our project page. Thank you for watching.